Hey everyone, Mr. Fransky here. Today we're going to talk about 5.2, which is an intro to the definite integral. And integral is a big topic in calculus that you've probably heard of before. If you're like me, when I was in calculus, I was like, when do we talk about integrals? Well, here we are. We are made it to chapter 5. We've been talking a lot about derivatives, and now we're going to talk about integrals, and eventually we'll get to how they kind of relate to each other, which is pretty cool. So let's jump right in. First, I have some bell work for you, which is about using LRAM, right? We talked yesterday about those rectangle approximation methods. So you need to think first about what f of x is going to look like. So it's a 4 minus x squared. It's going to be some kind of a parabola. I would think about where the roots are, if it's upside down or right side up. And you're going to approximate the area below f of x and above the x-axis using LRAM with 4 equal subintervals. If you want to try that on your own, you can. I'm going to jump right in and do it. So this is going to be an upside down parabola. It would have a y-intercept of 4, so we go up to 1, 2, 3, 4. And it would have intercepts at 2 and negative 2. 2 and negative 2 right there and right there. There's going to be an upside down parabola, something like that. And we're told to find the area below f of x and above the x-axis. So I'm looking for this area kind of right in here, right? The area that's created by this parabola and the x-axis. Sometimes I say enclosed by the parabola and the x-axis, something like that. So we use 4 equal subintervals. Well, that should be pretty easy. It looks like each one's going to have a width of 1, right? Because we have 4 units here, so we have a width of 1 with each. We're going to use LRAM. So I'm using the left corner of each subinterval. So let's focus kind of on this subinterval first. So the left corner is going to go up to here. Be something like that. So there's one rectangle. Now the next subinterval is going to go all the way up to the top. Looks something like that. And this one would look something like that, right? So I'm using the left side of each subinterval. I'm running that up to the function, and that's creating these rectangles. How about this guy over here? What would this rectangle look like? I don't think it would have any height at all, because the left side is right at 0, so it wouldn't have any height at all. So all we have to do is add these 3 rectangles together. So this area is going to be approximately equal to, I'm going to use squiggly equal signs because it's not exact. We're using an approximation here. We're going to have, the first one will be 1, which is the width of the rectangle, times 0, right? And actually, I'm going to write this out with function notation first, because this tends to confuse people. So it would be 1 times f of negative 2. So we think of f of x as 4 minus x squared here, right? And then it'd be plus 1, which is the width of the next one, times f of negative 1. Plus 1 is the next width, right? They're all width of 1, times f of 0. Plus 1 times f of 1. Right? That's it, right? So we have 1, 2, 3, 4 rectangles, and we're using the function to be able to figure out the height, right? Because the height is according to the left side, and in this case, that'd be f of like negative 1, right? And so each one has a function value, a height, and a width. So that is, I can use a straight equals now, because I'm going to say what this approximation is equal to. So that would be 1 times f of negative 2. If you plug negative 2 in here, you get 0. Then it'd be plus 1 times f of negative 1. F of negative 1 is 3. And then it'd be 1 times f of 0, which is 4. And then 1 times f of 1, which is 3. So 3 and 3 are 6, and 4 make 10. Not exact, but it's probably going to be pretty close, right? Now, all this extra area here maybe will kind of compensate for this gap over here. But all we have to do is, if they tell you to do an approximation, you do an approximation. That's it. Sometimes they give this to you in a table or something, and you have to be careful about the width. But if they tell you to use equal subintervals, then you just say, well, it's a width of 4 divided into 4 pieces. Each one is 4. Or each one is 1, excuse me. All right, moving right along. So can we get better? So obviously this is not perfect, right? And we talked about this a little bit in 5.1, but the question is, how can I get better and better and better? Well, let's kind of focus on, I'm going to kind of make a shape over here. Let's say I want to find the area underneath this curve. So this idea of using rectangles is good, but we talked about on 5.1, we said that the more rectangles we have, the better, right? So you might start with just like a few rectangles, so maybe like something like this. Okay, so this isn't a whole lot. I'm doing LRAM here, but you could do RRAM or MRAM, doesn't really matter, right? And then if we keep adding more rectangles, okay, so if I make these, like maybe I double the number of rectangles, okay, so if I double the number of rectangles, then they'd be skinnier, right? They'd be half as wide, so it'd be something like this. Okay, so notice those gaps are smaller, right? So the more rectangles we have, the better. What we want to do is we want to get to a place where we have an infinite number of rectangles, okay? So more rectangles is better. So more rectangles. Yay. Now let's think about how, what this area is actually going to be, right? So if we think about this being split up into n rectangles. Okay, so we have n subintervals. Okay, and usually you say this is from A to B, something like that, so it's on closed AB. Then how wide is each rectangle going to be? Well, if you think about it, the distance from A to B would be B minus A, and I'm splitting it into n subintervals, so if I wanted to find how wide each one of these is going to be, it's going to be B minus A over n, right? And usually what that's called is delta x. Okay, so delta x is the change in x. That's how wide each rectangle is. If I was to look at one of these rectangles, right, the curve would be kind of coming up here, maybe on the left side or the midpoint of the right side. So this guy right down here is going to be delta x, which is equal to B minus A over n. And the height is going to be equal to the function height, right? So what I'm going to do is I'm going to say that each one of these, there's like an x1 and an x2 and an x3 and an x4, right? I'm kind of getting crowded here, but you get the idea, right? Each one of these x coordinates along the bottom, it has a subscript. And then the height of the rectangle will be f of x sub k. Okay? So x1, x2, x3, x4, x5. The convention for this is that you actually don't use x, because each one of these x's will be prescribed, right? Because you can actually figure out what they are using the width of x. So it'd be a, and then a plus delta x, and then a plus 2 delta x. So usually what you use here is a letter c. That's what I'm going to do. Okay. So what we have down here then is c1, c2, c3, c4, like that. So c1, whoops, c1, c2, c3, all the way up to cn. Right? And the idea is that we have as many of these rectangles as possible. So the area of one of these rectangles is going to be the base, which is delta x, multiplied by the height, which is f of ck. Now, sometimes people get bogged down here with, well, is it a left side, a right side, or a midpoint? The answer is, it really doesn't matter, because if you're going to end up with an infinite number of these rectangles, they're going to be so skinny, right? They're going to be so skinny that eventually that it's just going to be like a line going up there. So it doesn't matter if you're using left, right, or midpoint. It's always going to end up just kind of being like somewhere random in the middle, right? So you could think the ck is just some random value in the middle of the rectangle, and as those rectangles get skinnier and skinnier and skinnier, it's going to end up just being the height of the line, right? The height of the line that's there. Okay? So then the overall area, the total area here, the total area of all these rectangles would be the sum from k equals 1 to n, because we have n of these subintervals, right? Sigma notation, maybe you haven't seen that in a while. And then it's going to be f of c sub k multiplied by delta x. Okay? This is the way it's usually written, right? That would be the area of all those rectangles added together. So then the area that is actually under the curve would be the limit. Well, limit's coming back again. Look at this. The limit as n approaches infinity, because we want as many rectangles as possible. Sum from k equals 1 to n, right? So we want n to get as big as possible. So we're going to have an infinite number of these rectangles. F of c sub k multiplied by delta x. Okay? This is the actual area underneath the curve. That's not a very pleasant limit, right? That's pretty gross. So what we do is we use a different notation for it. So if we are trying to find the area between the curve and an axis on a closed interval AB, where delta x is equal to b minus a over n. Okay? So notice there are no a's or b's in the actual limit. That's because delta x is just defined as splitting that ab up into n different subintervals. So this limit, as n approaches infinity, sum from k equals 1 to n of f of c sub k times delta x. You don't have to know this limit at all. There's a couple homework problems about it, but that's the last time that you ever see it. So what we do is we just, instead of writing this whole mess every time, we write this as what's called the definite integral from a to b of f of x dx. Okay, dx we've seen before, right? We've seen dy dx before. That's like a small change in y divided by a small change in x. It's a slope of a curve, right? dx here is just going to be a small change in x. So if you think about that curve, what you have here is you're saying that width right there is just a tiny little dx. It's very, very small. Infinitesimally small is what we say. So let's kind of break down what's going on here. So the a and b here, these are all limits. This is called the lower limit. That's where you start. And then this b at the top is called the upper limit. I should do this in a different color. Let's do that so that you can kind of distinguish between what's going on here. What are we going to use? Let's use green. Okay, this guy down here is the lower limit. This guy, this b up here, is the upper limit. Upper limit. This guy is called a definite integral. Talk about indefinite integrals in chapter 6. Okay, this is a definite integral. This f of x right here, that is our function. And it's important to note here, this x is what is called a dummy variable. Okay, this x is called a dummy variable. What that means is that it doesn't matter if it's x or t or y. You can use any variable you want. The calculation is always the same. Okay, so this means that it could be f of like t dt, that you see that a lot with parametrics. It could be f of y dy. Could be f of some other variable, I don't know. Theta often comes up in trig, f of theta d theta, something like that. The function on the inside here is called the integrand. It's what you're integrating. Okay, so integral. We integrate functions to find the area between the curve and the axis. Okay, so this sum, this infinite sum, we represent with an integral instead, because this is a gross limit. We don't want to write that a bunch of times. So we just use this, this fancy-looking integral instead. So what do you say? This is the integral from a to b of f of x dx. Okay, so I'd say I'm integrating from a to b. This is the integral from a to b of f of x dx. So the dx just tells you that you're integrating along the x-axis. So what the heck does this find, right? What the heck does this actually do? What it does is if you have a function, something like this, and you have a here and b here, it's this exact area. Okay, that area right there is equal to the integral from a to b of f of x dx. Okay, so this is our function f of x. So what we focus on for much more of chapter 5, and certainly in chapter 6, is how to evaluate this area, right? Right now, all we know is that you can do it with a bunch of rectangles, but how to actually solve, like how to actually find this area, requires what's called the fundamental theorem of calculus, which we'll talk about in 5.4. For now, we're just going to kind of focus on some simpler ideas or some simple things, simple ways where we have shapes that we know how to find the area as far as finding these definite integrals. Yeah. Sometimes that limit, because we really did this with a bunch of really skinny rectangles, so we said it was a limit as the number of rectangles goes to infinity. Sometimes you also see that as the limit as the delta x turns into 0, right? Because really what's happening is the width of these rectangles is getting smaller and smaller, and that as that happens, it turns into this dx, which is just an infinitely small little change in x, right? So really there are rectangles hiding in here, but they're so skinny that they have a tiny width, right? That really doesn't amount to much of anything, but it's just enough. So really all you're doing is you're taking the length of that line, which is the function, you're adding an infinite number of those lines together. And it doesn't turn into infinity because we have a closed area here. It's a finite area. All we really have to know right now is that this integral represents that area. So what kind of functions can we do this with? What kind of function, what do you think it would require for a function to be integrable? Well, you might have some ideas already, right? We talked about differentiable functions, we talked about continuous functions, so what does it mean for a function to be integrable? Well, let's take a look at some choices. So let's see if some people automatically say, well, it must be differentiable to be integrable. Well, let me ask you this. Is this function integrable? Could you find that area? Well, sure, absolutely, right? So it looks like it doesn't necessarily have to be differentiable, right? But this function is what? It's continuous. So here's the deal. Continuous functions automatically are going to be integrable. If you have a continuous function, integrable, no problem. Okay? If you have discontinuities, things get a little bit dicey, right? So if you tried to like integrate across a vertical asymptote, we're actually going to talk about this in chapter 8. There are some vertical asymptotes that you can integrate across, which is weird, right? But for now, we're not going to focus on those. But continuous functions will definitely work. There are some discontinuities, though, where you kind of have to think about it to decide if it's going to work or not. How about a jump? This one always throws people for a loop. Okay, this would be 1, 2, 3, 4. So my question is, could I integrate from 0 to 4? I guess maybe it'd make more sense to go from like 1 to 4. But could I integrate from 0 to 4 of this function? This function is a step function, f of x dx. Okay? A lot of times people say no. They're like, well, if you jump, then what's the value right after it? But the answer to this actually is you can do this just fine, right? So how you would do this is you would find the area of each one of these little rectangles. So this area would be 1 plus 2 plus 3. It'd be 6. This kind of gets into what we're going to talk about in a second, is using geometry to do these things. But it doesn't necessarily have to be integrable. So the converse of this is not true. And all integrable functions are not necessarily continuous. But if it's continuous, right now, that's what we're going to focus on. Is if you have a continuous function, it's for sure going to work. We're going to be able to integrate it. But there are some situations where it doesn't have to be continuous. These infinite discontinuities, those are a little weird, right? Also, like removable discontinuities, we'll talk about this later, but it's actually possible to integrate across a hole, right? And the reason is because the line that would go through that hole is infinitely small, right? There's no width really. So that one spot right there, you just integrate straight across it, and you just pretend like it's not there, which is kind of weird. Right? So let's try some examples. So like I said, this is the only time you see this notation, and it's really easy. Let me show you what you do. So in this case, we have our function in the middle here, f of c sub k. We have our delta x. K is always going to run from 1 to infinity, right? This does not have anything to do with the a and the b, right? And I think I should actually have some limits on these. Let's see. Yes, this is on 1, 9. I'm going to say, if I don't have those, then I can't do it. And this one is going to be on, I don't even know if I have one. Well, let's make it up. Let's say it's on pi 7, something like that, okay? So to write things in integral notation, all you have to do is just rewrite it with an integral. So this guy right here is going to be the integral from 1 to 9, right? Because we're going from 1 to 9, secant squared x. So instead of writing ck, right? Because what that means is they're picking an infinite number of little c's, and they're going to give the height of the function at different places from 1 to n, and that's going to be a dx. That's it. That's all there is to it. You just replace the c sub k with an x, and you're done. That's it. Try the next one on your own. See if you can do it. Let's give it a shot. So it's going to be integral from pi to 7, 3x squared minus 2x plus 5. You need parentheses here. The reason is because this is a product. You're multiplying a height of a rectangle, so a height h, which in this case is 3x squared minus 2x plus 5, by a width dx. So you have to multiply them. This guy up here doesn't need them because there's no addition, right? It's just secant squared x dx. So it's all a multiplication, not necessary. But anytime you're adding or subtracting inside an integrand, you absolutely need that dx at the end. All right, let's see what we got next. Ah, yes. Love this. We're going to evaluate some integrals using geometry. So, oftentimes, we're going to learn a lot of tricks for how to evaluate integrals, and people end up forgetting how easy it can be to use geometry for some of these things. So like, for example, the integral from 2 to 5 of 4 dx. So 4, if I just graphed y equals 4, or f of x equals 4, what would that look like? I think it would be a horizontal line at 4, right, like that. So what they're asking me to do here is to integrate that function from 2 to 5. 1, 2, 3, 4, 5. Here's 4. There's my function. So from 2 to 5. Well, how can I find that area? It doesn't require a whole lot of thinking, right? It's just a rectangle. In fact, this is a square. No, not quite a square, right? But it's going to be 3 times 4, which is 12. That's it. That's all there is to it. Next up, we're going 2 to 5 of x dx. So let's see here. So x dx looks like this, or x, just y equals x. So 1, 2, 3, 4, 5. So we're trying to find this area right here. Think about how you could do that. There is a formula for finding the area of this. We're actually going to talk a lot about it later in chapter 5. But what I would do is I would split this into a rectangle and a triangle, right? So the base here is 1, 2, 3. This little height right here, let's see, this would be 2, 2, this point right here. So the height here is 2. So the area of that guy is 6. And now this triangle, so this would be 3 and 3. So it'd be 1/2 times 3 times 3, which would be 9 halves. 9 halves plus 12 halves is 21 halves. Okay, so just using geometry to be able to find these areas, right? And that's the area of that guy right there. Next one, we got 3x. So, and we're going to integrate from a to b. So if we have 3x, that's just going to be a steeper slope. So if we have a here, we have b here. I'm going to do the same thing we just did. Okay, so I'm going to split this guy into a rectangle and a triangle. So the base here is going to be b minus a. This little rectangle is going to have a height right here. This corner is going to be 3a. So that'd be a comma 3a. I'm just using the function to be able to get that height. So it'd be b minus a times 3a. That'd be the rectangle. Then the triangle, let's see, this point right here is going to be b comma 3b. So then the height of this triangle right here is going to be 3b minus 3a. 3b minus 3a. I'll keep these separate here. And then the base will still be b minus a. So this is the rectangle right here. And then the triangle, so we have to add to it, is going to be 1/2 times base times height. So b minus a times the height, which is 3b minus 3a. I'll just leave it like that. Right? In terms of a and b, that will definitely be the area from a to b underneath that curve. This might be a formula that you don't see a lot. Think about it this way. If y is equal to 1 square root of 1 minus x squared, if we solve this a little bit, so if we square both sides, we have y squared equals 1 minus x squared, and then add x squared to both sides, we get x squared plus y squared equals 1. That might ring more bells. What is this graph? You might not remember, but it's a circle. This is a circle. And when you solve it the other way, you get a plus and minus because you get the top half of the circle and you get the bottom half of the circle. This is just the top half. This is a semicircle with a radius of 1. This is a semicircle with a radius of 1 that's centered at 0, 0. So it'll be something like that. We're integrating from 0 to 1. So we can just use the quarter of a circle. So it's going to be a quarter times pi r squared. So a quarter times pi times 1 squared, which is going to be pi over 4. This is an equation that comes up a lot for the rest of the year. Definitely good to know that equation for a semicircle. Next up, we got absolute value of x. Looks like this. -2 right there to 1, 2, 3, 4 right there. So we have two triangles here that we have to add together. So this triangle over here, 1/2 times base times height. So 1/2 times 2 times 2 plus 1/2 times 4 times 4. Half of 4 is 2. Half of 16 is 8. That is 10. Awesome. So evaluating using geometry, really not bad at all. You just have to think, what does this function look like, and then how am I going to piece these different pieces together? Sometimes you have to use like a rectangle and a triangle. Maybe you'll have some circles involved. One tricky thing that does sometimes trip some people up, they'll put like a semicircle, they'll raise it up, something like this. Remember, the definite integral finds the area from the curve down to the axis. So if it was something like this and they were integrating, you would have to find the area of the semicircle and also the area of the rectangle underneath it. Just be careful, it's the area from the curve all the way down to the axis. So everything we've done so far has had these nice function values that are all on top of the x-axis. So the question now is, what if f of x is negative? Well, what would that look like? That would look something like this. So if I have f of x down here, and I want to integrate from a to b. Well, what do you guys think? Based on how we've been evaluating this, if I wanted to focus on this point right here, and I think about this as being a rectangle, right? Delta x is up here, but what about my f of x value? What about my f of x value there? What can you tell me about it? It would be negative, right? I'd have a negative f of x value times a positive delta x value. So if you have area underneath the x-axis, so any area under the x-axis, is going to yield a negative integral value. Negative definite integral value. Now that seems kind of odd to begin with, thinking about like, how can area be negative? Well, the area isn't negative, it's that the function values are negative, right? So you have a positive change in x multiplied by a negative function value is going to give you a negative definite integral value. So if you have everything underneath, it's going to definitely be negative. Where this kind of gets interesting is if you have a function that changes, so something like this maybe, and you want to integrate from a to b. So now you have some that's above, you have some that's below, right? So what's going to happen is you take the positive parts, those are positive, and the negative parts you take away. So it's possible for an integral to be 0, which is kind of odd. So if you're integrating from a to b of f of x dx, all you do is you do the positive area and you subtract off the negative area. No, I should say the area above and below. That might be better to say. So the area above, whoops, and then you subtract the area below. I'm going to look at one example of that, and then we'll be done. So we want to integrate these guys. So x minus 4. So x minus 4 is the line y equals x moved down 1, 2, 3, 4. So something like that. And as you can see, there are parts of it that are below and parts of it that are above. So we integrate from 0 to 4. 4 is right here. So integrating from 0 to 4, that is all underneath. So it's going to be a negative value. When you do the geometry here, sometimes you have to remember at the end, but it's got to be negative because it's underneath the x-axis. So integral adds up the area between the graph and the x-axis. So this is going to be 1/2 times base times height, which is 1/2 times 4 times 4. And it's going to be negative because it's underneath the x-axis, solely for the reason it's below the x-axis. So negative 1/2 times 4 times 4, it's negative 8. Now if we went from 4 to 6, well, 6 is over here. So just going from 4 to 6 is a triangle with a base of 2 and a height of 2. So 1/2 times 2 times 2, positive this time. Why? Because it's above the x-axis. So what we have going on here is we have this negative part below, and we have this positive part above, right? So integral, so we have 1/2 times 2 times 2, which is a positive 2. So if we want to integrate from 0 to 6, we have the negative 8 part over here, and we have the positive 2 part over here. So that's going to be negative 8 plus 2, which is negative 6. Overall negative because there's more area below than there is above. How far would I have to go to get this to cancel out to be a 0? Well, we have 4 here. I think we have to go to 8. If you integrate it all the way to 8, you would have the same area above and below. That integral would be 0. So integral from 0 to 8 of x minus 4 dx will be equal to 0. Cool. All right, ladies and gents, that is all I have for you for 5.2. I'm really looking forward to getting into our properties of integrals and talking about the fundamental theorems soon. Love you guys. That's why I'm here. Have an excellent day.